Today's episode is brought to you by Engineering.com, a globally trusted source for engineering content. Check out this and many other exclusive videos for the engineering professional found only on Engineering.com TV today. Welcome to the Primary Loop. You know, the transition to an all-electric future is widely touted as necessary and inevitable. Now, to make that transition happen, two fundamental things are needed: energy generation and energy storage, especially in the form of transportation, which depends on the storage factor, as does the practical application of intermittent generation sources such as wind and solar energy. Now, current battery technology is limited by physics and chemistry, but better solutions are under development. Joining me on the loop is Moshiel Biton, CEO of Addionics. Moshiel, you have a PhD from Imperial College in London, I understand, so you come at this from a fundamental sort of scientific as well as engineering perspective. Tell me, the electrochemistry of batteries, it has been a hot subject for over a century. Thomas Edison complained about the hype around advanced chemistries in batteries at this point. It's lithium now. There are alternatives for transportation batteries where weight matters at this point. Are we stuck with lithium?
Yeah, I believe there are still lots of ways to improve lithium-ion batteries, and they are still going to be around. So we cannot say goodbye to those type of batteries. Of course, like alternatives will start to emerge, and it will be like a gradual transition, but it's not going to be overnight. And still, there are many years that lithium-ion batteries will play a dominant role in our electrification era.
Yes. Where is the intense research at this point? Is it electrodes? Is it anodes? Is it electrolytes? Is it insulators, dielectrics? Where's the action right now?
So, the activities in all those areas, in all the components of the battery. Traditionally, most of the focus was on the chemistry of the battery, on the active materials, the anode, cathode, and less on the inactive material and the electrolytes, current collectors, binder. But we see now lots of exciting technologies on the inactive component, which was some of them were overlooked, like the current collector. And that's something which is quite exciting because I think, like you mentioned, that it's old technology, which is true, but also it's very complex system. And this complex system is very shaky. If you change something like one parameter, everything has become unstable. So this industry is very traditional. People are scared to make changes. And that's, I think, there is a need of focusing on all the aspects of battery in order to have the complete improved solution.
Now, in the transportation sector, of course, transportation batteries are particularly difficult to engineer because they lead a rough life. There's a demand to charge them with very, very high current loads to decrease charge times. They're physically in an environment where there's plenty of vibration, shock loads sometimes. And I've seen some experimental batteries which use very fragile electrodes, anodes, which of course are clearly designed for a very great surface area, but you wonder about the durability. Is there an engineering trade-off between how tough you make the battery basically and how sophisticated the conformation is?
Correct. I think there are lots of trade-offs in batteries, and always it comes with trade-offs, no free lunch. When you improve one parameter, there is a trade-off or negative effect on the other parameter. I think the most exciting solution right now that are minimizing those trade-offs. You can improve one parameter without negatively affect the other. And yeah, it comes with higher energy, so it's affect the power. When you have a bigger battery, it will take you more time to charge the battery, but of course we'll have like more energy. So if we're talking about transportation, so a greater range, but it will take you more time to charge the battery. So it's something that we don't do it. Usually when you trying to make very hard casing of battery, of course it comes with weight, and this is a reduction of the energy density and of course the range of the vehicle.
Now, historically, and I'm old enough to remember when lead acid batteries were common in things like industrial forklift trucks, and we could simply charge at linear rates or we could taper charge, very, very simple strategies. Then nickel cadmium technology arrived at this point, a more sophisticated charging strategy necessary to avoid overheating these batteries. These new battery technologies that we're talking about that you're working on, do they require a more sophisticated charging algorithm or charging strategy, or can we just plow current in these things as hard and fast as we want?
I think that there are always a combination of these sophisticated charging protocols, but also I think the need of a solution, a physical and electrochemical solution that can enhance batteries to face extreme fast charging are needed. At the end, it's not enough to do the charging software protocols. You need to have like a structure that will be suitable to have those fast charging. It's a shock for the battery. It creates lots of heat that is generated during the charging that needs to be dissipated. Otherwise, it will cause like fast degradation. What's one of the, I would say, a very severe thing that's happening during fast charging is, of course, degradation of the battery, which, of course, we want to prevent.
Now, in traditional technologies like lead acid, things like heat buildup could be relatively simply addressed. You physically constrain the plates, essentially. You allow them to expand and contract as necessary, and everything is fine. Are thermal effects at issue here? Because some of the fast charging used, especially for transportation batteries, are putting in significant amounts of current in a very, very short time. So heat rise has got to be a factor. Are there mechanical, physical issues involved with these new battery technologies?
Yeah, definitely. There are plenty of effects, I would say, due to the fast charging. It's very aggressive. And yeah, there are some solutions to face with those challenges. Many solutions are, I would say, external solution on the battery, if we're talking about battery systems, so cooling, another solution on the system level. But I think fundamentally we need to solve some of the issues at the electrode level, cell level, and then to, I would say, scale it up. Then the solution is going to be more effective, and you will not need the super complex cooling or charging protocols in order to face with the challenges of fast charging.
What are the key considerations in electrode design specifically? Is it surface area essentially? Is it mobility, ion mobility? Often I've wondered, the catalysis people, for example, they have a big problem with catalyst poisoning. Are there enough active sites available so that they can actually get a reaction going there? What are your challenges at this level?
Yes, I think in the electrode there are many mechanisms that affect the lifetime, the durability of the battery. So you need to have very good adhesion between the active material to the current collector, and all the vibration that's happening in the battery, volume expansion, shrinking, cause to elimination, cracks, and of course to capacity loss. So adhesion is very important factor. Conductivity, thermal conductivity, electronic conductivity, super important to reduce resistance and to make sure that you have a very high and good conductivity. And also ionic conductivity is important. You want to have like a very good weighting of the electrolyte with the active components. And that's something that many companies working in order to improve it and to make sure that the battery will be with higher performance, reduce cost, and last longer.
Now, wetting is a phenomenon which is almost never discussed in popular discussions about battery engineering. So this is a surface energy effect?
Yeah, I think that like surface, it's well-known phenomena. It's not new. If you increase surface, you increase the area of the electrochemistry reaction, and you can enhance the kinetics of the phenomena in the battery. So it's well known, it's not new, the phenomena existing for many years, and we know that from other electrochemical devices like supercapacitors. And I think that the key is not just to recognize the phenomena, but to execute and to make sure that you can bring technology to the market that can be mass produced at low cost at high scale, and to be agnostic to battery application format, chemistry, something that will be generic like a platform, and to integrate into existing manufacturing processes. It's quite important. Lots of capital being poured into these infrastructures, and you don't want to bring innovation or solution without utilize the existing capex.
Moshiel, final question, and you anticipated it with that answer, in fact, which is the gap between the perfect electrode and then the mass-producible electrode. We could probably use, chemical vapor deposition or some electron beam epitaxy or something to create incredibly sophisticated sort of products, but they're just not scalable in mass production scale. Will the necessity to mass produce these things by the millions, will that be a constraint in developing the perfect electrode?
So, right, I think the optimal solution is a solution that can improve the electrode, but without the complexity of using very expensive tools, equipment, processes. You mentioned some of the processes that are already in use in mass production for semiconductors, but batteries are commodities. You need, as mentioned, millions of them to produce millions of them a day at a competitive cost, and that's a challenge. And in order to face that challenge and to make sure to compete with current technologies, you cannot increase cost. And that's number one, I would say, advice that I will give to anyone that wants to tap into that space, that the baseline is, okay, you need to make sure that cost reduction is number one. You cannot add any additional cost based to any sophisticated process. No matter how good it will be, you'll not be able to commercialize that, because at the end, you need like a market demand, and the market is used for certain cost and prices. And maybe for a niche application, it's something that can work, but at the end, battery market, the EV, the electrification revolution, we're talking about the massive market that need to commoditize like a solution.
Yeah, terrific. Dr. Moshiel Biton, CEO of Addionics, thanks for joining me on The Primary Loop.
Thank you very much.
And thank you for watching. See you next time. Well, that's it for this episode of The Primary Loop, brought to you by Engineering.com. For our deeper engineering series, visit Engineering.com TV for exclusive shows like Manufacturing the Future, Designing the Future, and the Engineering Roundtable, not found here on our YouTube channel. The links are in the description below. Thanks for watching.